Full screen. Good afternoon, all. I am Mr. Anirban Chakraborty. I am presently pursuing my postdoc research from Indian Association for the Cultivation of Science. And today, I would like to present some key findings of my PhD work, the topic of which is synthesis of ferroelectric glass ceramics, evaluation of crystallization kinetics, optical dielectric, and its ferroelectric properties. Now, to begin with a very brief introduction, so ferroelectric materials are a special class of dielectric materials which usually represents a spontaneous polarization on application of an external electric field, and the polarization gets reversed when the direction of the electric field is reversed, which gives us the hysteresis loop of this kind, as you can show from the figure. Now, depending on the type of hysteresis loop or the hysteresis behavior, ferroelectric materials are classified as ferroelectric, antiferroelectric, reluctant ferroelectric, reluctant antiferroelectric, paraelectric, or a linear dielectric material. And as you can see that with increasing of the domain size of the crystal size, the hysteresis behavior changes or increases. Now, there are various technological applications based on the ferroelectric behavior of materials, mainly of which it is in the non-volatile random access memories, ultrasound transducers, fire and vibration sensors, electro-optic modulators. However, the major drawback is most of the ferroelectric materials contains lead as its substituents, like in the lead zirconia titanates, which is mainly used in the industries for electrical applications. Also, this poses serious environmental hazards that causes hazards in the disposal and degradation in ferroelectric properties with cumulative polarization switching. Also, the European Commission in 2002 adopted a resolution that the hazardous substances like lead, cadmium, and mercury should be restricted for use in the electrical components. Now, so what is the way forward? The possible solutions are the lead-free perovskites and a new class of materials, that is the bismuth layer structure ferroelectrics. Now, for my work, I mainly chose these three materials, that is the barium bismuth tantalate, barium bismuth niobate, and the calcium bismuth tantalate systems, to be prepared in the glass ceramic route for the very first time. And as you can see from the table, that these materials have a very high dielectric constant, high remnant polarization, and very good fatigue endurance. As you can see, this is the representative crystal structure of these systems. That is the perovskite layer is sandwiched between the bismuth oxide layers. The advantages of these BLSF systems are that they have a very low aging rate, high resistivity, high remnant polarization, a very good thermal depolling performance, high QT temperature, and most importantly, they are environment friendly. Now, why did we choose these systems to be prepared in the glass ceramic route for the very first time? It is because, as you can see, that preparation of a glass through the melt quenching technique usually offers a simple, high-speed and low-cost preparation technique. Preparation of glass ceramic from glasses following the maximum nucleation and control growth allows us to produce a homogeneous and porphyry microstructure which leads to low dielectric losses, and such that we can control the crystal sizes and prepare transparent glass ceramics for photonic applications. high EB, that is the dielectric breakdown strength of the glass matrix in combination with the high dielectric constant of the ferroelectric ceramic phase and lower dielectric loss allows us to obtain high energy densities and moderate electric fields. So, transparent ferroelectric glass ceramics can suffice the need for photonics and energy storage applications. Also, energy storage technologies based on these lead-free ferroelectric glass ceramics can be developed that can be vital for the future of a clean energy landscape. And this is a review paper, that is a book chapter that has been recently published on this topic. Now, without wasting much time, our main research objective was to optimize the composition of these glass ceramics containing the ferroelectric crystal phase, since this is being prepared for the very first time, to analyze the thermal properties of the synthesized glasses using the non-isothermal DSC studies, to analyze the rate of crystallization from the kinetic studies at various temperatures, and optimization of the heat treatment protocol from crystallization kinetic studies such that we can achieve transparency in these systems. To analyze the influence of nucleating agent, now this is very important, like zirconium oxide or titanium oxide, for improving the rate of controlled crystallization, and such that we can improve the degree of crystallinity and control the extent of crystallization for better results. Also, to analyze the phase evolution microstructure of the glass ceramics and evaluation of these optical, dielectric and ferroelectric properties. Now, every new systems comes with various challenges. For these systems also we face some challenges, mainly of which it is that the synthesis of base glasses with this desired ferroelectric composition. This ferroelectric composition have very low to moderate glass forming ability. So this was a primary challenge to synthesize vitrified glasses with this composition. Also, we witnessed uncontrolled grain growth and high crystallization rates in the onset and the crystallization peak temperatures. And the synthesis of glass ceramics with controlled crystallization was also a difficult task. Now, what are the solutions which was adapted to minimize these challenges? That is optimization of the composition of the glass matrix and the ferroelectric phase by several trial melting. Crystallization kinetic studies method was adopted to study the rate of crystallization at different temperatures, such that the crystallization temperature can be selected for controlled crystallization, and the use of nucleating agents in the glass composition to promote homogeneous nucleation and crystallization. Now, as you can see, these are the three glass blocks that have been prepared. Now, let me mention here that bismuth oxide is the major component of these systems, and bismuth oxide has a tendency to reduce to metallic bismuth particles at high temperature. So, in order to control the autothermal reduction of bismuth, we use cerium 4 oxide basically as an oxidizing agent in these systems to arrest the autothermal reduction of bismuth ions to metallic bismuth, and we could obtain these transparent glasses or the condensed glass blocks. All the composition were melted around in an average from 1350 to 1480 degrees Celsius, and annealing was done from 480 to 630 degrees Celsius. And these experimental techniques were adapted for various characterization techniques. Now, coming to the first system, that is the ferroelectric barium bismuth tantalate glass ceramics. Firstly, we taking the base glass, we did the non-isothermal crystallization studies, and from the non-isothermal studies, the thermal properties were analyzed and calculated. The two most important parameters that were obtained were the reduced glass transition temperature and the Hubble parameter, and both the reduced glass transition temperature value is less than 0.58 and the Hubble parameter value is less than 0.5, which initially indicated that a possibility of bulk nucleation can be initiated in these systems. So, since it is a system which has been firstly prepared in the glass ceramic route for the very first time, we were interested to give a heat treatment at the crystallization peak temperatures. However, we could see that the deformation of the glass sample occurred, and the XRD of the sample was also performed, and it showed the BBT as a major crystalline phase for this sample. So, since the sample got deformed, we were more interested to study the crystallization kinetics in details, and the crystallization kinetics was studied through this the model fitting approach of the Kissinger, Augustine, Tozawa, and Matushita, which are known as the linear model fitting methods, and a model fit Friedman method, which actually calculated the activation energy of crystallization throughout the reaction, and from the optimized kinetic parameters. From the optimized kinetic parameters, we could obtain the rate of crystallization at various temperatures, and as you can see, at 700 degrees Celsius, the rate of crystallization is quite sluggish, which allowed us to control the crystal size and led us to synthesize the transparent glass ceramics till 6 hours of heat treatment, and thereafter it became translucent to opaque. The XRD analysis of the base glass and the glass ceramic sample, base glass showed amorphous sump, and the glass ceramic sample with an increase in the soaking time at 700 degrees Celsius showed that BBT has the formation of the major crystalline phase. Photoluminescence spectra of the European 3+ ion in this glass ceramic showed high photoluminescence intensity compared to the base glass, and the luminescence intensity increased from the base glass to the glass ceramic samples. Microstructure of the glass ceramics were also analyzed, and we can see the spherical microstructure, polycrystal type microstructure in this glass ceramics. The dielectric constant also increased from the base glass to the glass ceramics, highest being at 180 for the 30-hour heat-treated sample. However, to our surprise, we could see that the dielectric loss did not decrease much in these systems, and the dielectric loss in the glass ceramic sample was somewhat higher compared to the base glass. That is why we were interested to remelt or reanalyze this system by the addition of nucleating agent zirconium oxide with an aim to improve the degree of crystallinity, the microstructure, such that the dielectric loss can be improved, and also, as you can see from this system, that the polarization behavior of the hysteresis loop obtained is very lossy. And this one with 5 mole % zirconium oxide, we could obtain a quite better and very a better relaxer type of ferroelectric behavior loop. So with zirconium oxide, double stage and single stage heat treatment was adopted, and the polarization behavior greatly improved from the undoped to the doped system. The dielectric loss also largely improved from the base glass to the glass ceramics with a minimum of 0.002 for the double stage heat treatment sample. Now, similarly, coming to the second system, that is the calcium bismuth tantalite based glass ceramics. In a similar approach, the crystallization kinetic method was adopted, and the thermal parameters were analyzed to calculate the activation energy of crystallization and the rate of crystallization at various temperatures to obtain this transparent type glass ceramics. The refractive index of the base glass and the glass ceramics were analyzed through Cauchy dispersion fitting, and the refractive index, as we can see from this figure, increased from the base glass to the glass ceramics due to densification, and various other optical properties such as third order nonlinear optical susceptibility also increased from the base glass to the glass ceramic samples. The dielectric constant also increased due to progressive evolution of the non-centrosymmetric CVT crystal phase, and the polarization behavior was also better in this. The ferroelectric hysteresis loop behavior was also quite better for this type of system, and minimum dissipation factor of 0.001 was obtained for the 18-hour heat-treated sample. Now, coming to the last system, that is the barium bismuth niobate glass ceramics.
We are out of time, so jump to the conclusion.
Okay. Okay. So this was also the system which was prepared through zirconium oxide, and we could obtain transparent glass ceramics, as you can see. As you can see from this figure, with quite better hysteresis behavior, dielectric constant and dielectric loss. So the future aspects of this system is that to improve the dielectric and energy storage properties of these systems, so efforts can be taken to study the polarization mechanism at the interface, and optimization of the fabrication process is also required in order to modify or reduce interface area between the glass and the ceramic phases, and also choosing the glass matrix composition in such a way so that the optical transparency become independent of the average crystal size, and macrocrystals can be generated in the matrix. In such a way, the glass ceramics, the transparent ferroelectric glass ceramics can be prepared, which can have application in the as a capacitive energy storage as well as in photonics. So these are my publications and the number of citations over the last 4 or 5 years. So I would like to thank my mentor, Professor Roshini Ghosh. Now I am as my NPDF mentor, my supervisor, PhD supervisor, Dr. Atiyar Rahman Mullah, under whom I completed this my PhD work. I would like to thank UGC for providing me with my PhD fellowship, and ACRB and DST currently for providing me with the funding of NPDF. I would like to thank Indian Association for the Cultivation of Science, CGCRI, and Jadavpur University for all their support. Thank you.
Okay, so we have time for maybe one question from the audience. There's no question, so probably this means that the talk was very clear. So let's thank again Dr. Chakrabarty.
Thank you, sir.
And I will please welcome on stage Dr. Sharma. Anshu Sharma. She will give us her presentation on magnesium oxide and lanthanum oxide for supercapacitors. Okay? I think so. Is it open?
Hello, good afternoon everyone. Myself Dr. Anshu Sharma. I am working as an assistant professor in Department of Physics, Central University of Haryana, Mahendragarh. Today I am presenting the work magnesium oxide and lanthanum oxide based GCA and PPY nano composites for supercapacitor electrode applications. So these are the contents of the talk. I would like to describe about my current research and introduction, and all the parts will be here. Presently, our group is working on the nanomaterials for clean energy and environmental applications. In this, we are working in gas separation, gas sensing, and hydrogen storage applications. And we also working on the nanomaterials for energy and environment application. Basically today I will focus on the energy storage applications. Means we have prepared some nano composites which can be used as a supercapacitor electrode material, and some basic introduction about the topic. Everybody knows that energy is required for each and every technology, and we can say that industrial revolution is making the demand of energy increasing, and it leads to the deficiency of the fossil fuels, and there are so many renewable energy resources through which we can find out the energy storage, but we need to store the energy, and there are the option of capacitors and batteries, but we can look here that how supercapacitors are better than batteries. This is the basic of capacitor. Here we have capacitor. We can just store energy, means you can store charge in between two electrodes. But this capacitor is the basic device which is in which two electrodes are separated by an dielectric material. And why supercapacitor is super over the capacitor? You can see here the differences. Very low capacitance in the capacitor, but we can store very high capacitance in the supercapacitor, and we have low energy density in the capacitor but very high energy density in the supercapacitor. A supercapacitor is also having high power density. So if we compare supercapacitor with the battery, we can say that faster charge and discharge rate we can have in the supercapacitor over the batteries, and we have higher power density and lower energy densities, and lifespan is the main important part of the supercapacitor over the batteries. So supercapacitors are mainly of three types. These are electric double layer, pseudocapacitors, and hybrid capacitors. I will talk about in detail in further slides. Electric double layer capacitors, these are basically based on the storage of charges with electrostatic process, and pseudocapacitors are based on the storage of charges in electrochemical process. And in the hybrid capacitor, we can see that we can use both EDLC and pseudocapacitors. This is the charge storage mechanism. You can see here in the electric double layer capacitance, we have capacitance that is due to the charge separation at the electrode and electrolyte interface, and capacitance in the pseudocapacitance arises due to the reversible Faradic redox reaction. And this is the main concept of the supercapacitor. One can understand that supercapacitor are having these three parts. Main is the electrode material. The electrode should be very high specific area material. It should have high electrical conductivity, and it should have appropriate chemical stability. And electrolyte is the second component of the supercapacitor. We can say that it should have a wide operating window, higher chemical and electrochemical stability it should have. And third point is the separator, that is in between electrode and electrolyte. It should have porous structure, and it should have high permeability, non-flammable, and high ionic conductivity should be there in the separator. And another point of the supercapacitor is the charge collector. High mechanical strength and high electrical conductivity is the property of the current collector. So here I am going to represent my experimental work. In this we have synthesized the ternary nanocomposites which are based on the magnesium oxide and lanthanum oxide. Here we will discuss two type of nanocomposite that will work as a supercapacitor electrode. One is lanthanum oxide, that is doped in graphitic carbon nitride, and polypyrrole is also doped. And second one is the MGP, that is magnesium oxide based nanocomposites. So in the picture we can see that how polypyrrole, which is having the high electrical conductivity and high specific capacitance, and it is doped inside the graphitic carbon nitride, and we also doped the low specific surface area and good redox properties of the lanthanum oxide, which we have doped inside this, and we have made two ternary nanocomposites, that is called LGP and MGP. So this is the synthesis process of LGP nanocomposite. It is simply the graphitic carbon nitride was simply synthesized with the calcination route, and these nanocomposites of polypyrrole, GCN and lanthanum oxide were prepared using in situ polymerization reaction. In the steps we can see here, first GCN is synthesized based with the urea, and then LGP and MGP composites have been synthesized using the in situ polymerization reaction. These are the basic steps which are used to synthesize these nanocomposites. And simple process for the MGP nanocomposites, in this we can choose doping concentration according to the application part. And first we synthesize GCN, then we dope MGP. We dope magnesium oxide in this graphitic carbon nitride sheets. This is the process for the synthesis. These are the steps. Now come to the results and discussion. First is the XRD. In the picture we can see that X-ray diffraction is showing the major peak of the GCN at 27.5. That confirms a 002 plane which attributes the carbon nitride. And in the second graph, you can see that LGP composites are there with the diffraction peaks at 27, 33, 35, etc., which confirms the presence of lanthanum hydroxides. And we can say that from the XRD, it is clear that how lanthanum oxide is converted into lanthanum hydroxide by absorbing the moisture. And with the graph of the polypyrrole, we can see that the peak at the 26 degree represents the present of polypyrrole, means properly ordered chain, and the broadness of the peak represents the amorphous nature, and increase in intensity in a given reflection shows the preferred orientation of the composite. So XRD indicates the composition of LGP, lanthanum oxide, and this is the X-ray diffraction for MGP components. And in this graph it is clear that on increasing the concentration of magnesium oxide, the intensity peak at 27 degree increased and peak become narrower, indicating the transformation of the amorphous material into the crystalline material. So small peaks of magnesium oxide are also observed for different concentration of the magnesium oxide. Next is the field emission scanning electron microscopy. In the picture we can see that in the A part, that is the graphitic carbon nitride, GCN, and we can see the layered structure of GCN there. And in the second picture we can see that by doping of the LGP, means doping of the lanthanum oxide, there is improvement in the globular structure of the polypyrrole, and it is also noted that the grain size effectively reduced from 82 nanometer for LGP composites while maintaining the porous and spongy structure of the PPY. Means the conclusion is, if we are doping lanthanum oxide inside the graphitic carbon nitride, so it is improving the structure of the polypyrrole. And this is a Raman spectroscopy which clearly indicates the presence of lanthanum oxide peaks, that is at 3600, which demonstrate the OH group, which is showing that after absorbing the moisture, lanthanum oxide is converting into the lanthanum hydroxide, and polypyrrole peaks are observed at 1345 and 155 centimeters, which are similar to D and G band gaps of the graphene, which confirms that the lanthanum oxide is properly doped inside the graphitic carbon nitride. And in the Raman spectra of MgP2 in the magnesium oxide composites, the intensity of the D and G band gap, G and B bands increased manifolds. This includes the incorporation of the graphitic carbon nitride and magnesium oxide that has a significant impact of the pi conjugated bonds. Means we can see that how the charge transport properties of the composite that can make a potential electrode material to MgP. This Raman spectroscopy concludes. And these are the TGA, which shows the thermal stability of these nanocomposites, how and at what temperature LGP and MgP is thermally stable. So weight loss occurs till 200 degrees centigrade in LGP nanocomposites. In graph B we can see, and after 450 degrees centigrade weight loss is due to the decomposition of the polypyrrole chain. And in the MgP composites we can say that stability till 475 degrees centigrade. It is confirming the presence of graphitic carbon nitride in this MgP components. And this is a BET measurement just to find out the pore size and specific surface area of these pure graphitic carbon nitride polypyrroles. But after doping, what is the effect on the pore size? Because for the supercapacitor electrode, main property is the specific surface area of the material. So we need to find out whether the doping of the lanthanum oxides and magnesium oxides affects the pore size and pore volume of these basic graphitic carbon nitride sheets. So here we can see in the pictures,
Doctor,
and this table shows.
Please switch to your conclusion. We're out of time.
Just
Sorry.
a moment. So this table concludes the effect of the surface areas, and these are the main cyclic voltammetry measurements, which shows that the specific capacitance of the lanthanum oxide composites reaches up to 1763. Means we can find out that specific capacitance can be increased with the help of doping of these lanthanum oxide materials, and on increasing the doping concentration, specific capacitance first increases and it decreases. So it can be used as a good electrode material, and this is the GCD measurement for the lanthanum oxide and for the MgP, and this also shows that on increasing the current density, discharging time, and thus specific capacitance decreases due to the constraint of the ion diffusion and an incomplete charging discharging of the electric double layer within time frame. So this is the EIS spectroscopy, which indicates also that the diameter of the semicircle gives a value of RCT. Means we can find out that these material are suitable for supercapacitor electrodes, and these are the conclusions. Means this work concludes that lanthanum based graphitic carbon nitrides and magnesium oxide based composites, these are simply synthesized in C2 polymerization reaction, and specific surface area is highest, resulting in increased pore size. That concludes that these are worthy materials for the electrode material for the supercapacitor application. And the main thing is the higher specific capacitance of lanthanum oxide shows that if we dope lanthanum oxide or magnesium oxide in these graphitic carbon nitride, then these nanocomposites are suitable material for superelectrode applications. I would like to acknowledge Sir DST for the following projects and UGC for the projects for funding. Thank you everyone.
Okay, so no time for question left. Sorry, so we go ahead directly to the next speaker.
Thank you.
Thank you. Which is Dr. Sagadevan, which will present nanocomposite photocatalysts for wastewater treatment. Is Dr. Sagadevan present? No? Suresh Sagadevan. Yeah, okay. Okay.
Can you hear me? Yeah, I connected now.
Yes, we can hear you. Welcome.
Oh, thank you, Chairperson. Thank you so much. Very nice to meet you. So, can I share my slides? Can you see my slides? Can you see my slides?
Yes, yes.
Okay. Can you see? Uh, okay. Thank you. Thank you once again. Thank you. Uh, good evening, one and all connected here and presented here. So, I'm Dr. Suresh Agadevan, working as an associate professor in Nanotechnology Catalysis Center, University of Malaya. So today I'm going to talk about that nanocomposite photocatalyst for wastewater treatment. Why I am, we are working on that photocatalyst for wastewater treatment. This is needed because you know that water is polluted due to that by dye wastewater. Because many countries have the textile industries, they used for very dangerous organic dyes, especially methylene blue, methylene orange, and rhodamin B. So these dyes are very dangerous. Then the dyes are mixed with the drinking water. When you drink the water, we have a lot of health issues. So this is our main concern to how to solve this problem. This is very important and a very global problem. Nowadays, you see that air polluted and then water polluted, it's everywhere polluted. So we need to solve these problems. So we can use for this some catalysis, especially for nanocatalysis. The photocatalyst is an environmental friendly method that can be applied to degrade the variation of organic dyes pollutant in this wastewater. So this is our concern. Then we choose this research based on that two nanocomposite for potential catalysis for this wastewater treatment applications. You can see that how the major water pollutant from these various sources. You look at here the sewage and human and animal extract, and then that the example is a bacteria and virus, and the sources is the agriculture, domestics, and industrial wastage. This example is pesticides, oil, plastics, and detergents. These categories we can call it as the infectious agents and as well as the organic chemicals. The same this another the sources of you look at here day-to-day life, we are using the domestic and industrial wastage, which means that acids and salt, metals. This is an example. And mining power plant, the natural resources, the example is the uranium and thorium. So these are two categories under this of inorganic chemicals and as well as the radioactivity material. So very major water pollutant for this, the plant nutrients, and then example for this nitrite and phosphates, the sediments like salts and soils. These are two category of under this source of chemical fertilizer, sewage, and manure and soil erosions. And as well as you look at here, this is thermal and oxygen demanding. This oxygen demanding, the example for heat is most of the heat is dissipated in the form of this any thermal plant, and as well as the agriculture wastage of manure. So this is for these sources from this industries and power plant and sewage and agriculture runoff. So how to solve these kind of issues? All of you know that there's a nanotechnologies play the vital role for this technology development. So we can use for this nano composites. The nano composites are fabricated by basically two methods. So one is a top-down approach. The top-down approach is well-known method. You know that the bulk material broken to the smaller size, which means that is mechanically force is involved. For example, you want to make it as a smaller particle, just smaller the things, you make crush it manually. You can crush it, or if you want to make powder form, we can use for missions like this. We want to make it some kind of nano size of powder. We can use for ball milling technique to reduce the size in the smaller scale. That method we can call it as the top-down approaches. And bottom-up approach is very quite challenging and very quite interesting also. That one is we can controlling this size and size in the chemical due to the chemical reactions. We can controlling the size, growth of agglomeration of this atom. So this method is, we can call it as a bottom-up method. Bottom-up method is usually we can call it as the chemical reactions, sol gel, hydrothermal process, wet chemical and chemical reactions. Many methods are there. So why these nanomaterials always have unusual properties? Because you can look at here, when you look at the bulk material, you can see that how that surface area and then other properties, especially for electron band gap and magnetic properties, because this conference is related with the physics. So all of you know that a lot of physics people attending this conference, you know that usually we can use many of the devices made up of from that, especially for semiconductor devices. We are using for this semiconductor material, silicon, germanium, arsenic. But now
so Dr. Suresh, sorry to interrupt you, but the slide sharing is not working. So
okay, yeah. Now okay, clear?
Okay, now we see that you're on slide number, I don't know, 12.
Okay. Thank you.
Okay.
Please, due to the technical error, yeah, please you can tell me, then I can change. So you look at here how that changing these properties like surface area and then antibacterial properties and hardness, electron band gap, electric properties, all properties are superior when compared to this bulk material. This is the advantage of nanotechnology. You look at here, you see that here different properties like catalytic and electrical, mechanical, optical and magnetic properties. So all properties when compared to this bulk material, it shows that is, you look at that electrical properties increase the electrical conductivity, and as well as mechanical properties, you look at that improve the hardness and toughness of this metal and alloys. When you reduce the size from bulk to nano, you will look at that the changes of this kind of properties. So that when you using for this kind of nanocatalysis, usually nanostructure photocatalysis material that can be used to break this down the pollutant in the wastewater through the process called the photocatalysis. So you look at that, some example I given here is very interesting. How to synthesize, I mentioned that the first slides about different methods are involved to prepare this kind of nanomaterials, and then also the type of nano materials. Like carbon-based nanomaterials, when you mix with metal oxide combined with that any graphite or graphene, so we can call it as a CNT, carbon nanotubes, so we can call it as the carbon-based nanomaterials. And also some kind of nanomaterial, combined with the polymers, so we can call it as a polymer-based nanomaterials. And then different metal oxides, and then metal green synthesized metal nanoparticles. So many kinds of classification of nanomaterials can be used for this wastewater treatment application, and also it can be to enhance this catalytic activity. Why this is what is the motivation for this structures? Because the reason is, you look at here, what is the reason? Because when you're preparing for this kind of nanomaterials, you will get diverse morphologies with a different shape, rod shape, spherical shape, cubical shape. This is one advantage. And also the other advantage is a high theoretical capacity and simple preparation method. We used for very low cost and very economical method. it is very easy to synthesize for nanomaterial. And another important advantage is a high catalytic activity, and also we can use to enhance this high degradation percentage. So main advantage of nanostructure is the important things: high surface area, morphologies, and wide band gap. So the first I'm going to discuss about that fabrication of graphite carbonated. Before my lectures, she also prepared for this graphite carbonated with other metal oxides. But we prepared for graphite carbonated with cuprous oxide for this composite enhance this catalytic activity. We used to for this very industrial organic dyes for dyes for these organic pollutant of degradations. Look at here. This is a synthesis of graphene carbonated composite. Is very simple but hydrothermal method. As of all of you know that this is a graphene carbon sheet, and then we took that 100 ml of ethanol and sonicated for 15 minutes. This is the cuprous oxide, is a heptadal shape, and combined together for 180 degrees Celsius the solutions, and kept it that hot air oven. After 180 degrees heated for 12 hours, you look at here, we got this composite graphene carbonated with cuprous oxide composite. After this composite, we studied for this physical chemical characterization like XRD and FESM, DLS, DRS, UV visible. And also this our aim is concentrated for this photocatalytic degradations. We used for this, as I mentioned, that very important for industrial organic dye, methylene blue, and rhodamine B, thiamal blue, blue ink. The first we have to confirm this composite and material. How to confirm this composite and material? By using for this physical chemical characterization, especially for these X-ray diffractions and FTIR, both which is confirmed this successful.
Please, we have to ask you to wind up a bit because you are already 12 minutes presenting, and in order to be quick, really. Are you still with us, Dr. Suresh? We can call him next. You can call the next speaker. Yeah. Okay, so Dr. Suresh, if you're still there, please give us a sign of life. But we move on with the session. So we call our next speaker, which is probably Dr. Shidaling Mattepanavar, presenting unusual metallic behavior at low temperature, high pressure structural and thermoelectric studies of delta silver sulfur selenide and titanium scandiate single crystal. Are the speaker here?
Yes, sir. Yes, sir. I am here.
Welcome.
Thank you.
So, doctor, stay strict in your 10 minutes. 10 minutes.
Yes, sir. Yes,
okay.
Sir.
Thank you.
So, my PowerPoint presentation is visible to all of you, sir. Yes, sir. Am I audible?
Try to move one slide and get back.
Yes, sir.
Everything is fine. Start your presentation. Thank you.
Sir. Good evening, all of you. Good evening, session chairman and organizers, for giving me a chance to present my work. So, I am Dr. Sidling Mattepanavar. The title of my presentation is Unusual Metallic Behavior at Low Temperature, high pressure structure and thermoelectric properties of delta, AZ4SSC and thallium single crystals. So this is the outline of my presentation. So first I would like to give a brief introduction about the thermoelectrics and superionic materials. Then I will address the problem, and then I will explain the synthesis method and few highlighted results with conclusion. So this is the introduction of the thermoelectricity. So all of you know that the importance of thermoelectricity at the current global problem due to the global warming. So here the thermoelectric materials are basically conversion of the thermal energy into electrical energy. So if you look at the industries, only the 60% of the utilized energy is being lost from the waste. And in that, if we implement thermoelectric materials in that industrial waste thermal energy, so at least it plays a significant role to save the some amount of some amount of electrical energy. So these thermoelectric materials basically we calculate on the basis of figure of merit, that is ZT. So here I have mentioned the equation that Z equal to S squared sigma by kappa total and then thermal temperature. So here S plays the Seebeck coefficient and sigma is the electrical conductivity and kappa is the total thermal conductivity. And to have a better thermoelectric material, one should have optimized the property of all these parameters. So for example, if you look at the right side of the here, that I have shown the one is glass and other one is the copper metal and one is the semiconductor. So the register I have shown. So basically the ideal thermoelectric material should exhibit low thermal conductivity like a glass material and high electrical conductivity like metals and high Seebeck coefficient like semiconductors. So usually we will not see all these three parameters in a single material, but if you have optimized the property of these materials, so then one can have a very good thermoelectric material. So these are the best well-known thermoelectric material, that is PBTC, GBTE, and BITOC, and SLT, and SEL. So to address this ideal thermoelectric material, superionics also plays a very important role. Why? Because superionics have a high electrical conductivity and it has a moderate Seebeck coefficient, and also it exhibits low thermal conductivity. So with this motivation, we have taken silver sulfur selenide system. So AG4SSC, so there was a paper was published very recently by Dobronsky et al. So they found that from the DSC measurement, two transitions, one is at around 375 Kelvin and other one is at near room temperature 280. So the 375 Kelvin, what they have seen, so that is maybe due to the structural transition from the monoclinic to cubic, but the transition which they have seen near room temperature, so that they say that this transition that could be the existence of charge density wave in this sample. And this claim was surprise to us to see the charge density behavior in this sample, and many of the charge density wave present sample shows that low temperature there is a superconductivity. So with that motivation, so we prepared this sample through a single crystal by chemical vapor transport method, and then we try to explore the structure around that transition, what kind of structural transition is happening, and then we have gone to the detailed electrical properties and then magnetical properties and come up with a very good, interesting new physics which was not explored earlier on this sample. And also we have studied the structure dependent, pressure dependent structure studies of the sample. And later on I will come to the how this sample can be exhibit low thermal conductivity, particularly I am talking about the thallium selenide single crystal. So this basically I am talking here about the two systems. One is Ag4SSC and other one is the PLSC. So both the systems are prepared with the different techniques. So the Ag4SSC was prepared by chemical vapor transport method, and thallium selenide single crystal was prepared by the Bridgman technique. So the synthesis conditions are completely different for the both the single crystals. And so this was the single crystal I am showing from the Bridgman technique. So this was the thallium selenide single crystal. So this is the structural studies of Ag4SSC. As the reported, this Ag4SSC exhibits at room temperature, it's a monoclinic structure, and from the room temperature to higher temperature, it goes from the monoclinic to cubic structure. But we are not interested in the high temperature part, and we are interested to see the charge density wave in this sample. So that's why we have studied the low temperature X-ray studies, basically synchrotron X-ray studies or high energy X-ray studies. And we saw that there is a surprising result that this compound shows very sharp transition around 250 Kelvin. So from monoclinic to it goes the orthorhombic structure with a very sharp transition at around 250 K, and all the atomic parameters we extracted by the fitting YANA software, and they showed that there is a clear structural transition is happening from the monoclinic to orthorhombic. And then basically we are interested to see how this structural transition affects the electrical properties. So here we can see that the where we are at room temperature, so the resistivity shows quite high, that is in the milliohm centimeter, and when it cools the system from 300 Kelvin to up to 2K, so we have seen that there is a sharp drop in the resistivity, and that after that drop, so this has continued. So initially we thought that there might be some kind of superconductivity, but up to 2K we have not seen any kind of zero resistivity in this sample. But if you look at that, the resistivity becomes almost linear from 250 Kelvin to up to 2K. So now with the further modification in this sample, so one can one can achieve that zero resistance in this sample with this structural modification. So basically what is happening here, so why this material is exhibiting such a sharp resistance, such a sharp low resistivity. So that may be the due to the Fermi structure reorientation has happened due to the structural transformation. So that's why this material exhibiting such a low resistivity. And we have also studied this right side part diagram, what I am showing, that is the magnetoresistance behavior at a few above and below the transition temperature we have taken. So the magnetoresistance also showing some kind of opposition or negative magnetization behavior when we are measuring the orthorhombic structure, means around the structural transition, it is showing the negative magnetization part. And this is the thermal properties we have studied. So we have arrested we have seen the all the structural parameter, all the structural transitions here. So the first blue line, blue color shows that the one is around 350K, so that is due to the cubic to monoclinic transition here, and one it shows from the monoclinic to orthorhombic. The red one shows that monoclinic to cubic, and this is the second one, second transition. And we have measured the specific heat capacitance from room temperature up to 2K. So we have seen that only one structural transition is happening at 250K. After that, there is no structural transition in this system. And this was the zoomed anomaly of the anomaly at the structural transition. And lower specific heat capacity data was fitted with the Arrhenius equation to extract the phonon contribution present in this sample. And then the most important part is the magnetization measurement. So we have measured the low temperature susceptibility measurement at different magnetic fields. So here we have seen that at various magnetic fields we have done, and all the external magnetic field, there is a sharp drop in warming and cooling cycle with a quite very good hysteresis slope. So this basically the hysteresis slope of this magnetization shows that it's a diamagnetic ordering or diamagnetic susceptibility. So it's a basically larger magnitude in the low temperature. So this was which was not observed in previously in AG486. This was the first time we have noticed this kind of properties in this material, and that's why this could be the maybe due to the diamagnetic diamagnetic susceptibility and lower density of state at the Fermi level, which leads to the decrease in the polyparamagnetic susceptibility. So that's why we call that this is the new transition. So that's why we named it is delta AG4SSC. So this phase was not observed previously. And then we have done the band structure calculation for both the structures, like monoclinic structure and orthorhombic structure. So band structure calculations well supports our experimental results. Here we can see that there is an overlapping of the bands when it goes to the orthorhombic structure. So also we have measured the spontaneous voltage generation in this sample. Around the transition, it is producing this spontaneous voltage generation. And then we are interested to study this material high pressure structure studies. So this high pressure structure studies was carried out in the Indus Beamline, Indus 2 in RRCAT. And here we can see that data as the pressure increases, so there are additional new peaks are coming up, and these new peaks are related to the orthorhombic structure. So even it goes when you are applying the pressure, so it is going from the monoclinic to orthorhombic structure. And the next material comes, that is the thallium cyanide single crystal. So this material, for the first time we have observed such a low thermal conductivity in this sample. So you can see here compared to some standard thermoelectric material like cobalt, antimony, and lead tellurium, tin tellurium, germanium tellurium, compared to all these samples, so this material exhibits very low thermal conductivity, and basically this material also exhibits the tetragonal structure, and here to exhibiting such a low thermal conductivity here, basically structure plays a very crucial role. So here the thallium existing in two ways. One is thallium present in +1 state and other one is the +3 state. And because of this +1 and +3 state, so basically +1 state thallium is playing a major role to reducing the thermal conductivity. So this is the X-ray diffraction path data, and here we have seen that tetragonal structure with I4 per LCM space group, and we have obtained the lattice parameter and compared with the reported values. And here you see that. So basically this material was prepared by the single crystal by Brisbane technique, and also we have made the SPS pressed material.
Dr. Matepanavar, we have to kindly ask you to wind up and jump to the conclusion because you are ahead
Yes,
of time.
Yes, sir. Yes, sir. Thank you. Sir. I will finish it. So this is why this thallium cyanide material is exhibited such a low thermocuplicity because of the presence of low optical phonon modes are present. So from the Raman measurement, we can see here that at around below 50 centimeter inverse, so it is showing two main broad peaks, and they are the basically main reason to exhibit low thermal conductivity, and it is confirmed from the terahertz spectroscopy measurement also. And these are the theoretical measurements. They are well supports our low thermal conductivity. And this is my conclusion. So overall, I can say that Ag4SSE in this sample, there is no charge density wave and superconductivity in this sample. So only thing is that the structural transition is happening with the Fermi structure reconstruction is happening. Because of that reason, such a low resistivity we are getting. And thallium cyanide is a very good low thermal conducting material. So this is my these are my details about the citations and H index from the Google Scholar I have taken. And these are my past supervisors. So I have done with single crystal in Beirut University, Professor Sander within Germany, and thermoelectric with the professor, my postdoc supervisor Kanishka Biswas, and my postdoc supervisor Professor S. Ramakrishnan, and high pressure studies done in BRC. And thank you for your kind attention, sir. Thank you.
Okay, so I say we move to the next speaker. Okay. So I will ask Dr. Sanjeev Sharma, which is present or online. Dr. Sanjeev. Sanjeev Sharma. Okay, so if he's not present, we move to the next one. Dr. Chander, Subhash Chander, presenting optimized properties and performance of all inorganic, I don't know how to pronounce it, absorber layers for flexible perovskite solar cells. Are you here? No? It's not present? Okay. So our last speaker for this session, presenting on a comparative study of extraordinary and ordinary mode in self-focusing of higher order modes of elegant Hermite-Koch Gaussian laser beams in uncollisionless magnetized plasma, Dr. Van Moor has raised an hand. He's over here. Dr. Bandopant Van Moor.
Hello.
Hello.
Hello. I'm audible, sir?
We can hear you.
Okay, sir. Okay, thank you very much, sir. Just I sharing my screen, sir.
I asked the clinician guys to. You can already share your screen.
Yeah, sure, sir.
Okay.
Sir, my screen is visible?
Yes, it's visible and it's moving.
Yes, okay. Thank you very much, sir.
Okay.
So, a very good evening to all of you. I am Dr. Bidwan More. I am assistant professor in Department of Physics, D.Y. Patil College of Engineering and Technology, Kolhapur. So today I am going to present an comparative study of extraordinary and ordinary modes in self-focusing of elegant Hermite Gaussian laser beams in an collisionless magnetized plasma media. So this is the outline of my presentation. So first we will see the introduction to the laser, then plasma media, then phenomenon of the self-focusing, then research method we have adopted, which method we adopted we will see or we will discuss, then graphical result and discussion is there. So see, this is the introduction of laser that we have used in our theoretical simulation. So after survey of literature, one become aware for there are many laser beams with variety of intensity profiles available practically. So depending on the geometry of cross section of laser beam and the intensity distribution of known by name special function, the laser beams are available as circular Gaussian beam, elliptical Gaussian beam, standard Hermite Gaussian beam, bigger Gaussian beam, basal beam, etc. All these laser beams explore to study the propagation dynamics in various nonlinear media. So in this present study, we have adopted the elegant Hermite Gaussian laser beam, and this is the field distribution of elegant Hermite Gaussian laser beam. So this is the normalized intensity distribution of elegant Hermite Gaussian laser beam. So here is the normalized intensity profile of the elegant Hermite Gaussian beam in first picture, figure 1. There is a transverse electromagnetic 0 mode is given. So here one more interesting thing is that we have one additional parameter, and that additional parameter is denoted as a B. So as we increases B, so this is the normalized intensity profile before entering the plasma media, how the intensity of that laser beam. So here the first picture in graph first, the decentered parameter while we kept it 0, this is the intensity peak. If we increase the decentered parameter B like this, so intensity will go away from go central from the axis, or it can be away from the axis. So here we can see in graph 2, if the B is 1, then intensity how is started to away from the central peak. So in this way, this is the graph third, that is the decentered parameter 1.5. This is the graph fourth, where the decentered parameter get again increased 2.0. So similar in this same manner, here we shown the transverse electromagnetic of 0 to mode of elegant Hermite Gaussian laser beam. It means again this picture shows that the laser beam or laser nature, laser behavior before entering the plasma media. Similar here I shown the transverse electromagnetic EM04 mode for elegant Hermite Gaussian laser beam. In all of these three pictures, we understood that the laser beam, while we increasing the decentered parameter, the laser central peak will be go from the axis. So then, introduction to plasma. We know that the plasma is one of the four fundamental state of matter, and other is being solid, liquid, and gases. So plasma is basically or electrically neutral medium of unbound positive and negative particles. That is, if we say about the charge of plasma medium, then it will be roughly 0. So this is the introduction to the self-focusing. Self-focusing is the non-linear phenomena in which the linear part is there and in which the non-linear part is also there. So here we can see the linear part and non-linear part. This is the refractive index to that medium, and this is the linear part of the refractive index. This is the non-linear part of the refractive index. So here the phenomena of self-focusing comes. So self-focusing is the typical type of nonlinear wave propagation that depends critically on the transverse intensity profile and laser beam. So for consideration, one may assume that laser beam is circular cross section and having Gaussian intensity distribution. So depending upon the nature of intensity and dependent nonlinearity, the sign nonlinear correction in this present figure becomes either positive or negative. Suppose here is the delta n, that is the refractive index. If suppose this is the positive, then the peripheral part of the laser beam moves faster than the axial part. As a result, wavefront of the laser beam becomes concave in the direction of propagation of the wave, and thus laser beam get focused on the optical axis. This is shown in figure number 1, and the defocusing is nothing but the exactly reverse situation is observed in the nonlinear correction is negative. If the nonlinear correction is negative, this is the central part of the laser beam moves faster than the peripheral part. Consequently, the plane wavefront of the laser beam becomes convex and the direction of the propagation of the wave, hence the laser beam defocuses. Here you can see the laser beam defocuses. So next, this is the hypothesis and theoretical approach we adopted. Our hypothesis is by controlling the two transverse decenter parameter, that is B1 and B2, along the X and Y direction respectively in the field profile of the laser beam. So it will be control or possible to control the shell focusing length in a plasma media or in a nonlinear dielectric medium. So in this theoretical study, we used a theoretical approach, that is Akamanov's parabolic wave equation approach under Wenzel-Kramer's Boolean and paraxial approximation. So this is the nonlinear dielectric constant. This is the dielectric constant. This is the linear part of the dielectric constant, and this is the nonlinear dielectric constant. So here is the collisionless magnetized plasma medium. We have taken the plasma medium which is a collisionless medium, collisionless plasma medium, and this is the intensity profile that we used for our simulation. So this is the wave equation. These are the important equation which we are using to solving the numerical solution for this ordinary differential equation. So these two equation is showing the second order ordinary coupled nonlinear differential equation. And if we take this solution of this equation, then we got the critical curve like this. So this is the critical curve of TEM02 mode. So here we specifically studied TEM02 mode. So figure 1 shows that this figure shows that the variation of beamwidth parameter with normalized propagation distance for TEM02 mode. So classified under extraordinary mode, this is the extraordinary mode, E mode, and this is the ordinary mode. It means the left circular polarized laser beam and right circular polarized beam. So for any given values of symmetric decenter parameter, beam width parameter shows oscillatory changes against the beam width parameter, and it decreases including the stronger cell focusing. Here we can see the stronger cell focusing, we found that. And and for both the mode in extraordinary mode and in also ordinary mode, with increasing the decenter parameter, that is the increasing the value of B. Here we can see B1 is for left X direction and B2 is for Y direction. But suppose if we increase the decenter parameter value, then we found that the beam width parameter F1 focuses over larger distance than the beam width parameter F2. And the minimum value of beam width parameter in both the modes do not differ considerably. In both the modes, if we say more specifically, in both the modes with the increase in the value of decenter parameter, the phase change in beam width parameter F1 is almost negligible. So however, with increase in the value of decenter parameter, phase change in beam width parameter F2 are significant. So it means here we can say in comparison of F2 with the comparison of F1 is more stronger and more self-focusing. So this is the conclusion. Here we conclude that for both the mode extraordinary and ordinary mode under symmetric as well as asymmetric decentered parameter, periodicity normalized distance of propagation of oscillatory beam width parameter, in particular both the mode beam width parameter shows the periodic variation and it travel over a long distance. So second observation, we found that in case of TEM00 and 02 mode under symmetric and asymmetric decentered parameter, the amplitude of oscillatory beam width parameter remains less than unity. It means because it's less than 1. And however, in case of TEM04 mode, amplitude of oscillatory behavior of beam width parameter becomes greater than the unity or 1. So also we found that the stronger self-focusing is observed in case of F1, which is traveling in X direction and than the Y direction. So complexity is also observed in the higher order modes during the propagation in elegant Hermite Gaussian laser beam through collision-less magnetized plasma medium. So these are the our observations. So thank you one and all for your attention.
Thank you, Dr. Bandapant.
Yes, thank you very much, sir.
We have time actually, so are there any questions from the audience or from the web for Dr. Bandapant? No question. So let's thank all the speakers of this wonderful session once again.
So, very much thank you for Dr. Michel D. Laura and Professor Ajay Nagar for conducting this session. Now, I would like to invite Dr. Alok Vyas for presenting a memento to Dr. Michel D. Laura. Thank you very much, sir. Now, I would like to request Dr. Michel D. Laura for announcing the result of this Young Achiever Award. So, please, sir. Result, yeah. Who is the first, second? Yeah, first. Yeah.
Yeah. So the best young awards, young presenter awards, goes to Dr. Chakrabarti, Anirban Chakrabarti, for his work on a synthesis of ferroelectric glass ceramics. Is Dr. Chakrabarti here? He left?
If anyone is here, you can take the memento. If anyone know Anirban Chakrabarti? No one? Okay.
Ah, okay. in absentia.
We will send them.
And also the second?
Yeah.
The second classified, but it was a very close run. Yeah. Okay, so they're almost equal. Is Anshu Sharma for her work on MgO and lanthanum oxide based for supercapacitor electrode. Dr. Sharma, is she here? No, she is not. This guy win and then they leave. It's fantastic.
So, thank you very much for conducting this session. Now we will, please Anirban.
You see, here comes the winner.
Please, we are waiting for you. Anirban, yeah.
Shall we give him some? You will give him? Wait, it's okay.
So please come on stage.
So we evaluated your performance at the festival today. Thank you.
So thank you for attending this session. Now we will conclude this session and we just move to the first floor for the parallel oral session. Thank you.
Thank you. Okay.
0 number 8.